In this video, we will begin our investigation into more advanced techniques of integration. So we will begin with kind of a recap as to where we are with antidifferentiation. So to begin, we have a list here of common antiderivatives that we should all know and quickly and easily be able to recall. Now, the only new formula on this list that we have yet to encounter would be the antiderivative of secant x. I have included this just to make sure that we have it on our radar, and it's something that will come up again in future videos. So along with these common antiderivatives, we have one more advanced method of integration at this point, which is substitution. So as a reminder, substitution is a technique of integration that undoes the chain rule of differentiation. So to evaluate an integral of the form given here, where the key characteristic that indicates a substitution is this function inside another function whose derivative appears outside. So function derivative pair. What we will do is let u be g of x so that du is equal to g prime x dx. And the big idea is that a substitution does not solve the integral, but what it does is expresses the integral in terms of a hopefully simpler, easier to evaluate integral. You evaluate that resulting integral, and then you resubstitute to get back in terms of the original variable. Let's look at a few examples. So to begin, let's evaluate the integral given here. And the key observation that I'm going to make is that seeing this ln of x inside another function and its derivative appearing outside of it is a giveaway that we might want to consider a substitution. So if we let u be equal to ln of x, du will be its derivative, 1 over x dx. So ln of x is u, 1 over x dx becomes our du. So immediately the integral, we have a 1/2 that we can pull out front, and what we are left integrating would be secant squared of u du. So the original integral that we started with appeared very difficult. But once we make that substitution, it becomes a much more reasonable integral for us to evaluate. So recall the antiderivative of secant squared is tangent. Because it's an indefinite integral, we need our plus c. And then the last step, as always with a substitution and an indefinite integral, is to resubstitute. Every spot we see a u, we replace it with a natural log of x. So 1/2 tangent of the natural log x plus c. For the second example, 2x squared over 2x squared plus 1. So immediately this looks like a rather difficult integral. And it doesn't look as though it's well suited for a substitution. And if it's not going to be a substitution for us, our only other choice would be some type of algebraic manipulation to somehow get it back in terms of those common antiderivatives. And the observation that I'm going to make is having the 2x squared in the top and a 2x squared plus 1 in the bottom is an indication of maybe how we can add and subtract the same quantity in the top to hopefully simplify. So what I'm going to do is take the numerator, which is a 2x squared, and we are going to add 1 to make it look exactly like the denominator, but we can't just add 1, so we need to subtract 1 as well. Once we have done this, we can now break this up into two separate fractions. We can think we have the 2x squared plus 1 over 2x squared plus 1, which becomes a 1, and then we are subtracting away, we have 1 over 2x squared plus 1. And this becomes much more reasonable. We can break it up into two separate integrals, the antiderivative of 1 minus the antiderivative of 1 over 2x squared plus 1 dx. So the first antiderivative is simply x. For the second, what I would like to do is compare it with one of the formulas that we saw earlier. And the formula I would like to compare this to is the antiderivative of 1 over x squared plus a squared is equal to 1 over a arctangent x over a plus c. Now it's not quite in the desired form. We want x squared plus a squared. So what I'm going to do is go ahead and pull a 2 out of the bottom. So if we pull a 2 out of the bottom, we have to rewrite 1 as 2 times 1/2. So it's going to be plus 1/2. And now it's exactly in the form that we see above, where our a squared is equal to 1/2, which is really 1 over the root 2 squared. So 1 over root 2 is our value of a. So substituting a in for that formula, the 1/2 is hanging out front, then we have 1 over a, so 1 over 1 divided by the square root of 2, multiplied by arctangent of x over a, so x divided by 1 over root 2, plus c. And just to simplify a small bit here, we have x minus, then we have 1/2 times 1 divided by 1 over root 2. That simplifies to just 1 over root 2. Dividing by a fraction is multiplying by its reciprocal, so square root 2x plus c. So keep in mind when it comes to evaluating antiderivatives, where we are at this point, we can somehow use substitution or use algebraic manipulation to get back to our common antiderivatives.